In this talk, I want to survey some work that's been going on for a few years now, designing kind of new algorithmic techniques and algorithmic primitives for processing massive graphs. So when people talk about massive graphs, there's some classic examples they often point to. Things like the call graph, where kind of nodes of the graph are phone numbers and edges correspond to phone calls that are made during a given period of time. The web graph, where nodes are web pages, edges are hyperlinks. The IP graph, social networks. One of the challenges of processing such graphs is that you can't really use conventional algorithms on graphs this size. So you often can't fit the graph in memory. The graphs may be changing over time. Graphs also arise not just in these kind of examples of kind of classic big graphs, but just in kind of any situation where you've got information about some basic entities and the relationship between these entities. So it's a way to encode structural information where you have data about both entities and their relationships. So examples include graphical networks, citation networks, protein interaction, and metabolic networks. So there's three main kind of computational models, very related computational models that are going to be relevant in this talk. They're going to be useful for processing these big graphs. And these three computational models are streaming, sampling, and sketching. And let me talk briefly about those. Let me just say one thing right now. Just like, even though I pointed to these examples of some big graphs, everything I say for the entire duration of this talk applies to arbitrary graphs. These are just kind of some motivational examples of big graphs. I'm not going to kind of there's a lot of really cool work on investigating properties of, say, social networks, but I'm not going to kind of use any specific properties of families of graphs, except maybe in one instance. All the algorithms I'm designing, all the algorithm primitives I'm presenting apply to any arbitrary undirected graph. Okay, so streaming, sampling, and sketching. So the streaming model has been around for a while, probably kind of over 20 years. In the last 10 years, people have started looking at kind of solving graph problems in the data stream model. And I'd say in the last 4 or 5 years, people have been looking at this particular model. So the input to your problem is a stream of updates to a graph. Like if there's a given node set, there's n nodes of the graph, and the stream is saying, can I add an edge between node u and v, remove the edge between node v and w, and you get a sequence of these updates to your graph. Okay? And if you had unlimited memory, you could just you could store all these updates. At the end of the day, you could just run you would have your graph in memory, and you could run your favorite graph algorithms from your favorite graph algorithms textbook. Instead, in the streaming model, you have the challenge that you have small memory. You have memory that's kind of sublinear in the number of edges of the graph. Sublinear means different things in different contexts. Sometimes we'll be allowed memory that's proportional to the number of nodes of the graph, sometimes less than that. Okay, so we get one pass through this data stream, small space, and we want to compute properties of this input graph as it arrives. So there's a bunch of kind of classic stream results. So the stream really starts off with looking at numerical quantities, kind of estimating kind of frequency moments, the number of, if it's a stream of numbers, the number of distinct numbers in the stream, computing things like medians and heavy hitters. So as I mentioned, this kind of growing body of graph streams looks at problems with more structure. And people have looked at problems like estimating distances in the graph, estimating the size of cuts, eigenvalues, emulating random walks, clustering, matching, dense components, various covers. There's now too much in the field to kind of do a good job reviewing. There's a survey that we put together a couple of years ago. However, this is now 2 years out of date, and people have done some cool stuff in the last 2 years. But that's the best reference I have to point to you at the moment. Okay, so that's streaming. Any questions about the model? There was a fair amount of streaming talks in the first week, so. Okay. Sketching. So the idea behind sketching, and I believe people talked about sketching the first week as well. The idea behind sketching is your input is encoded as a big long vector. This could be encoding geometric information or graph information, or it could be a feature vector in some high-dimensional space. And you want to process this vector. But the idea is, rather than process this big long vector, you first apply a random linear projection that projects down this long vector down to this short vector, and the hope is that if you've designed this random matrix correctly, that the properties of V that you want to compute can be estimated just by looking at the projection. Okay. So you can do this projection, post-process the projection, and get your answer. So there's many results on sketching or on linear dimensionality reduction for numerical statistics, for basic geometric properties. There's an extensive theory. There's connections to hashing, compressed sensing, dimensionality reduction, metric embeddings, etc. And this actually primitive is actually widely applicable. It's very useful in the data stream model because the idea is that as you go through the stream, you don't need to remember, you basically kind of implicitly encode your data as a vector, and you don't need to kind of keep that entire vector around. Rather, you can kind of keep around a projection of that vector, and every time you see an update in the stream, you can work out how does your projection change, rather than having to kind of reapply the entire projection onto your big vector V. And so the main question that's been motivating the work over the last 4 or 5 years is, well, sketching was great for these numerical statistics problems and some geometric problems. Like kind of, what utility could random linear projections have for the case of more combinatorial problems in the context of graphs? Like kind of, on the face of it, it seems like kind of, it might not be too successful, just because sometimes combinatorial problems can kind of depend on the existence or otherwise of a single edge. So really, kind of what could a random projection hope to do? But we'll see, actually, sketching has quite a lot of useful applications in the context of graphs. Lastly, sampling. The idea here is that you have your big input graph, and we want to develop ways to kind of maybe sample edges from that graph, such that we can tell interesting properties of the underlying graph. So the most simple way of sampling edges, I guess, would just be kind of uniformly. Like if you have m edges in the graph, I'm going to pick, I don't know, 100,000 of them uniformly at random, look at what I get, and try and say something interesting about the graph. This works for some problems. A recent result that kind of was simultaneously come up with by 3 groups was that if you take your graph, your undirected, unweighted graph, and you sample n throughout the talk is always going to be the number of nodes. So if you sample roughly n over epsilon squared edges uniformly at random, this allows us to estimate the maximum density over all induced subgraphs, where the density of an induced subgraph is just the number of edges in that induced subgraph divided by the number of nodes. It's not a difficult proof, but no, it requires a little bit of care, because you end up taking the union bound. It's a kind of it's a Chernoff plus union bound style argument, and you end up taking the union bound over an exponential set of subsets. You need to be a little careful, but it all works out. So that was uniform sampling, but we already know from other work that sometimes doing non-uniform sampling is very useful in the context of graphs. So for example, if we sample each edge E with probably roughly inversely proportional to the edge connectivity of E, then you can argue that you preserve all cuts in the graph up to a factor of 1 plus epsilon. So by edge connectivity, if E is just the edge UV, lambda UV is just the number of edge disjoint paths between U and V. So so I guess this would mean that if I have if there's not many paths between U and V, I sample this edge with very high probability, whereas if there's many paths between U and V, I would sample that edge with very low probability. So this form of sampling is great at preserving all cuts of the graph. If I replace this 1 over lambda E by what's known as the effective resistance, then I also preserve a whole bunch of nice spectral properties. So the idea behind effective resistance is you just take your graph, you replace every edge with a 1 ohm resistor, and RUV is basically the potential difference you get when 1 unit of flow is injected at U and extracted at V. Okay. So non-uniform sampling is sometimes the way to go. So the main questions that arise in sampling is, okay, here are a couple of examples. Are there other types of graph sampling that can be performed that would tell you interesting things about the graph? And also, like kind of, even though I'm presenting this as 3 different models, like kind of streaming, sketching, and sampling, at the end of the day, I really want everything to kind of it to be possible to implement it in the data stream model. So I'd quite like these sampling primitives we come up with. I'd quite like there to be a way to kind of to actually perform this sampling over a data stream, kind of using small space and quickly. Okay, so that's streaming, sampling, and sketching. So in this talk, I'm going to produce sketch-based algorithms for two classes. I'm going to overview some sketch-based algorithms for two classes of problems. Firstly, we'll look at connectivity problems. So we'll be using linear sketches to analyze edge and node connectivity, build spectral sparse files, etc. The main kind of take-home idea in this section is that linear projections give rise to kind of naturally give rise to a form of kind of homomorphic compression. By which I mean that you can take all your data, like kind of maybe the rows of the adjacency matrix of the graph. You can kind of compress them each down individually. And then whatever algorithm you'd want to run on the original graph, if you had unlimited space, like linear sketches give you a way to argue that you can run that original algorithm on the compressed graph. Okay, I'll make this more explicit in a few slides' time. Then the second section of the talk, presumably after the break, I'll be talking about matching problems. There's been a lot of work on this in the last year, including by people in the room. So we'll look at non-uniform sampling techniques for kind of exact matching graphs, for approximate matchings, and also for matchings in not arbitrary graphs, but maybe say planar graphs or graphs with certain properties. And the general theme there is like using a little bit of graph theory, cracking open some graph theory textbook. You can support interesting types of sampling via sketches that are useful for solving graph problems. As I say, these are all sketch-based algorithms. I'm not going to be too explicit with. My goal is really to present the kind of the core ideas, like kind of the core primitives. I'm not going to spend too much time saying, okay, well, this is how you'd actually. This would be the pseudocode for the data stream algorithm, or this is how you'd implement it. But my hope when I prepare these slides is that I'm presenting the stuff at a suitably high level of abstraction that. The ideas will be clear, and you can think about going to apply them in the data stream model or MapReduce or some other distributed model of your choice. Okay. Like my motivation in all this work has been getting things working in the dynamic data stream model, and all these algorithms will apply, but I won't always make it explicit. Any questions? Okay, cool. Okay, so part one, connectivity. To describe, and I apologize to the 3-4 people in the audience who've heard me talk about connectivity on multiple occasions. So to describe the connectivity result, let me kind of jump settings from streaming to something that's kind of a puzzle. You can formalize this puzzle via communication complexity, but you can think about it as more of a puzzle. So you've got n players here. I think this is the cast of The Social Network movie. And each of these players has an address book listing their friends amongst these n people you see on the slide. And the challenge they have is they just have the address book. They're not communicating to each other. What they get to do is they get to send a message to some third party, to, I guess, this lawyer here, with the goal that when this lawyer receives the messages from these n players, that she'll be able to work out whether the underlying graph was connected. Okay. Now, obviously, if everybody sends, like you could encode every address book perfectly in n bits. So if everybody sent n bits, we'd be fine. What we're able to show is that it's possible for everybody just to send polylog n bits. I think it's kind of log to the 3 is the best we've got so far, a bit message, such that with high probability, the lawyer can work out whether the underlying graph was connected. And yes, I want to kind of reiterate that there's no communication between these n players. They all just kind of communicate to this central player. I will, however, assume that they have access to public randomness. So is the theorem statement clear? Okay, great. Okay, if you think about the theorem statement a bit, you should probably start to doubt it for the following reason. Let's suppose we have a graph where we've got some densely connected component over here and a densely connected component over here, and we have these two players connected by a single edge. Okay, so the connectivity of this graph is hanging by a thread. Like, if this edge exists, the graph is connected. If it doesn't, it's not connected. Okay. So think about what these two players are now going to do. It would seem that at least one of them, in their message to the lawyer, needs to send omega n bits. Why is that? Well, the central player, this lawyer, needs to find out whether this edge exists or not. It seems to be. Because every player just has their own address book, they have a very limited view, very local view of the graph. So Eduardo here can't tell that this edge is any more special than any of these edges. Okay? So if he's to guarantee, and he may have omega n other friends, so if he's to guarantee his message has at least some information pertinent to this edge, you kind of think maybe from some sort of basic information theoretic argument, you could argue that he needs to send omega n bits. Or maybe if he didn't send omega n bits, then the other player, Cameron, I guess, needed to send omega n bits. So it seems like the theorem can't be possible. So one of my first goals in this talk is show you the theorem is possible. Or I guess people say that's proving the theorem. Okay, the basic idea is to use these kind of linear sketches. So Mark is going to kind of take his address book, encode it as a vector, and send it across, and send a sketch of it across to the lawyer. So of course, the big question is, well, we won't be able to just do any sketch. We'll need to kind of carefully design the sketch here to have some nice properties. Okay. And then this is where I want to kind of make this notion of homomorphic compression a bit more explicit, or at least show you a picture. So the idea is that the proof, the analysis of what we're going to do, the basic idea is that we're going to kind of design a sketching process and identify an algorithm such that instead of running the algorithm on the original set of address books, so say you have the original set of address books here to find the graph, and running kind of this algorithm and getting your answer, we're going to argue that it's possible to first sketch each of these address books. So each of these things are essentially n-bit objects. Each of these things are polylog n-bit objects. We're going to be able to sketch these such that if we run this same algorithm on this compressed data, we'll be able to argue that kind of every operation we want to do here is kind of supported in this kind of sketch space, and that we'll get the same answer with the same probability. Okay, so that's the general picture for what I'm hoping to do, and I'm going to make that even more explicit in the first technical section. So the main story for this first half, the connectivity story, has basically been a really nice sequence of papers addressing kind of problems related to connectivity, starting off with the first result I'm going to talk about, which a special case is just answering whether the graph is connected. More generally, if you want to test k-connectivity, so I guess connectivity is just like between every pair of nodes, is there at least one disjoint path, one edge disjoint path? K-connectivity, k-edge connectivity is between every pair of nodes, are there at least k-edge disjoint paths? So you can do this in order k bits with my O tildes omitting these polylog n factors. Okay. This was then generalized to not only can we kind of prove that result that polylog n bits are sufficient to answer whether the graph is connected. Like if you allow me to increase the communication by a factor of 1 over epsilon squared, then we'll be able to approximate every cut in the graph. This is actually kind of called cut sparsification, this ability to kind of approximate every cut in the graph. More recent work deals with spectral sparsification. So this includes, say, basically kind of approximating properties of the Laplacian of the graph, in particular the eigenvalues, and this actually also, you can prove this actually also preserves all cuts. Again, using roughly 1/epsilon² polylog n bits from each individual player. And then I guess most recently, this was all really focusing on edge connectivity. If we move over to node connectivity, basically, is it the case that there are k nodes of the graph that when I rip them out will disconnect the graph? That's testing k connectivity. You can do this using kind of roughly k² bits from each player rather than k bits from each player. There's some open questions here that are interesting, I think. Okay, so I'm going to talk about connectivity. I'm going to talk about edge connectivity, node connectivity, and then I'll briefly talk about sparsification. Any questions? Okay. Okay, so looking back at this picture, most of the things are going to follow this template. So really, if I'm going to present you an algorithm for connectivity, there's two main ingredients. I need to say, what is this connectivity algorithm we're going to kind of emulate in sketch space? And also, how do we do these sketches? Two things I need to tell you. So let me tell you those two things. OK, so the basic algorithm we're going to emulate, a nice simple algorithm, goes as follows. So it actually not just answers the Boolean question, is this connected or not? It actually kind of computes a spanning forest of the graph, or a maximally acyclic subgraph. So the idea is you have your graph. We'll pretend for a second this is a massive graph. For each node, we'll pick an incident edge. So maybe this node picked this edge. That edge was also picked by that node. So these three red edges were the edges that ended up being picked in this first step. When you've picked these three edges, you can note that there's two connected components of the graph. This connected component on the left, connected component on the right. And as a next step, for each connected component, you can then pick one incident edge from that connected component. With a graph so small, there's actually only one incident edge to these connected components left. It's this guy. So let's pick that. Once we've picked that edge, these two connected components merge, and we've got one big connected component for the entire graph. OK, so this was a small example with 5 nodes. In general, you kind of keep on going until this converges. If it's connected, it will all converge to one connected component. If I know there are k connected components, it would converge to k different connected components. What's nice is that no matter how big the graph is, if the graph is on n nodes, this process will terminate after order log n rounds. And the selected edges will include a spanning forest of the graph. Okay, so that's the simple algorithm that I hope to emulate in sketch space. So the idea behind designing the sketch is a little bit more tricky, but not terribly so. So let's kind of keep using this kind of toy example graph. And the first step we do is we associate every node in this graph with a vector. Node 1 gets associated with vector A1. And A1 is defined as follows. So if there are n nodes in this graph, there's going to be n choose 2 entries of this vector, corresponding to each pair of nodes in the graph. So we have 1, 2, 1, 3, 1, 4, all the way up to 4, 5. Okay? Now, most of these entries are going to be 0 of this vector. The only non-zero entries are going to correspond to incident edges for the relevant node. So node 1 has incident edges to 2 and 3. And so these two entries, 1, 2, and 1, 3, are both going to be 1. Everything else is going to be 0. Let's do one more. That's node 2. We're going to find a vector A2. So again, the incident edges are 1, 2, 2, 3. And the non-zero entries are 1, 2, and 2, 3. OK. So note that I've non-zero entries are always going to be 1 or minus 1. In the first case, all the non-zero entries were 1. In the second case, some of them were -1 and 1. The rule is going to be that if you're incident to someone with a higher label, you're going to be a 1. So 1's incident to 2 and 3. So these things end up being 1. When you're incident to someone with a lower label, it's going to be a -1. So 1, 2 in this case, 2 is incident to a node of lower label, so it's a -1. And this edge 2, 3 is a 1 because 3 is higher than 2. Okay, why am I messing around with these +1s, -1s? Well, this has the nice property that, okay, so given any AI, vector AI, I can work out the the non-zero entries correspond to the incident edges of AI. Because of these +1s and -1s, I have the property that if at some point I'm interested in, say, I have a connected component consisting of 1, 2, and I'm interested in the incident edges, the edges are basically across the cut from this connected component to the rest of the graph, I can find those edges by just adding together these two vectors. So I take A1, I add A2, some stuff cancels, and I'm left with non-zero entries of 1, 3, 2, 3, which are exactly the two edges across this cut. Okay? And this is like kind of more general. You can prove that for any subset of nodes S, if you add up the corresponding vectors, and you look at the non-zero entries, the support of this sum, then this corresponds exactly to the edges across the cut from S to the rest of the graph. Okay? The only other idea we'll need to design the sketch. Like, so far what we've done maybe sounds a bit crazy. Like, the whole point was trying to compress the address books. The address books were of size n, and the first step we've done is for every address book, or for every node, we defined a vector of length roughly n squared. This does not seem to be helping compression. So the second component of designing the sketches is using an idea from the data streams literature, which I'll use as a black box for the moment. If you're interested, I can unpack that black box a little bit in a second. So, actually, how many people are very familiar with compressed sensing? Okay, so enough people that maybe this description makes sense. So compressed sensing, you're applying a projection onto a vector, and you can to a much shorter vector, such that you can recover all the non-zero entries from the original vector based on the projection, on the assumption that the original vector is sparse. Okay? What we're going to do here, no promise about sparsity, and therefore the guarantee is going to be weaker. So the original vector can be arbitrary, but from the projection you're going to be able to find at least one non-zero entry of the vector. Okay? So unlike compressed sensing, this is going to be kind of a random matrix we're going to apply. So we're projecting down from big long vectors down to short vectors, such that if you give me any long vector, I will be able to deduce a non-zero element of that vector just by looking at the projection MA. Okay? Clear?
You mean with high probability?
Yeah, with high probability. Yeah, thanks. Any other questions? Okay.
Does this imply somehow that you can peel it down? So you can find one, you can remove the I don't know, effect of that. It seems too thin.
Yes, you cannot. And I think it's quite interesting how you cannot. I'm going to maybe allude to it briefly okay, I'm going to gloss over a detail. I'm going to have a footnote that kind of comes clean about the detail, and I'm more than happy to sort of talk about it at the break. Okay. But that's exactly the right sort of question you should be asking. Okay. So let me show you how we use that. We're going to use this lemma. So the message that your node I, the message you're going to send me is you're first of all going to encode your address book as vector AI, then you're going to apply the random matrix M onto it and send me M of your vector. And that's going to be a vector of length polylog n bits. Okay, and then let's see, I'm the lawyer, let's say. So you send me all your information, and yeah, so each player sends, the jth player sends M, A, J. So I receive all these sketches, and I can now think about trying to emulate that basic algorithm. So remember, the first step of the algorithm was for every node, identify one of the incident edges. That's something I can easily do now. Like when I receive MAJ, now remember M had the property that I was able to recover one non-zero entry from AJ, and the non-zero entries of AJ were exactly incident edges. So when Jelani sends me kind of his sketch, I can work out one of Jelani's friends. Okay. But then this is just for the first round of the algorithm. For every node, I had to find one incident edge. Like I don't want to I hope this doesn't come off wrong. I don't want to talk to you guys again. You've sent me your information. I want to be able to do all my subsequent post-processing just on the information you've sent me. Okay, but I somehow need to emulate these subsequent rounds of the algorithm. So how am I going to do that? So at some kind of arbitrary point in the algorithm, I will have a connected component S, and I'm trying to find an incident edge, or an edge across the cut from S to the rest of the graph. So I don't know, maybe I've just found out that all you guys to my right, are on some big connected component, and I'm trying to find one edge from you guys across to the rest of the graph. Okay. This is where the fact that the sketches are linear comes to play in a simple but maybe somewhat surprising way. So the idea is that I can take all the sketches you guys have sent me, and I can add them up. I literally take your vectors and I just add them up. Okay? Because of linearity, the sum of the sketches is the sketch of the sum. Okay? Because of the properties of M, I can now find a non-zero entry in the vector corresponding to the sum of your AI vectors. And because of that lemma in the previous slide, the non-zero entries of this sum of vectors correspond exactly to edges across this cut. Okay? And that's really it. So, at various points in the algorithm, I'm just asking for an incident edge from this connected component out. I can find that by adding up your sketches. And as I said, it just required one initial communication from everybody of roughly polylog n bits. Any questions?
I guess you need that the high probability is larger than 1 over n or something.
Great, okay. Footnote where I come clean about one issue. It doesn't change the, it only changes the result by a factor log n. So there's so as Riddicker said, I'm emulating, every time I ask something for the sketch, there's some probability of failure. This was a randomized algorithm. So we could argue that, well, I'm going to ask for an incident edge at most n times, and so the failure probability would increase by at most a factor n. Okay? If every time I ask for one edge, I have probability delta, it would be nice to say that since there's n steps of this algorithm, that the overall failure probability went from delta up to delta n. And so therefore, I'd have to make sure the failure probability was small enough so that this wasn't a problem. That's actually somewhat optimistic, because what I'm doing here is I'm very much adaptively using my sketches. So as Henri pointed out, even with this result, there's a potential this seemed a little too good to be true, because you could take your random sketch, pull out one node, and then maybe pull out another node and reconstruct the initial vector by just doing a series of steps. Okay. So the reason you can't do that is you cannot be adaptive. You cannot make adaptive queries with linear sketches. You cannot pull the union bound off. And so here as well, what saves you in this context is that you're emulating an algorithm only with log n rounds. So in each round, you're having a fixed set of queries you're going to ask about the sketches. By queries, I mean if you're summing up some sketches and asking something of them. But there's only log n rounds of adaptivity. And so to actually fully make the probability calculations work, what we need to do is that it's still just a one message that everybody sends to me. There's no interaction. But what you do is you don't send me just one projection of your vector. You send me log n independent projections of your vector. And then for the ith round of the algorithm, I will use the ith independent sketch you sent me. Okay? And then everything works out. But if you're with me up until this point, you've really got the gist of the algorithm. It is pretty much as simple as it seems. This is not complicated. This is just like, well, if you had to write down the proof, a formal proof for everything I've said, you would realize a certain issue, and you'd probably fix it in exactly the same way we fixed it. Okay, I can tell you something briefly about L0 sampling. So sometimes when I present this result, people are thinking, wow, okay, so L0 sampling must be, okay, sorry. This result, sorry, I didn't give it a name. Okay. This technique here, this thing which is a bit like compressed sensing but not, it's called L0 sampling in the data streams literature. So sometimes when I present this result and it all fits together so neatly, people think, well, there must be something really complicated and mysterious going on within L0 sampling. That's not the case at all. I can present the basic idea of L0 sampling. And in fact, Graham talked about L0 sampling, I think, on the second day last week. But just in case you need a refresher, so yeah, we want a random matrix that from this we can deduce a non-zero element from E. The basic idea is this random projection matrix has the kind of structure that the top row is almost all ones, the second rows are roughly half ones, the third row is roughly a quarter ones, the fourth row is roughly an eighth ones, so on, so on. And this means that whatever vector you throw at this projection, in this case it has 3 non-zero entries. Like kind of maybe initially, because you have many ones here, you have kind of all 3 things colliding in the first entry, and therefore you won't be able to kind of disentangle them. Maybe in the second entry you still have some collisions, like in this case I guess the x and the y kind of both kind of hash or both end up in the same entry. But at some point down, and towards the bottom, like kind of there's too few zeros for anything to arrive here. But at some point there's going to be a sweet spot where exactly one thing appears. And so there's a little bit of kind of engineering issues to get this all to work, but that is basically the idea of L0 sampling. So even though I was using it as a black box, and I hope that was okay, if you unpack the black box, it's really not that complicated, and yet I think you get this surprising result at the end of it, like kind of that everybody can just send a small number of bits. Okay, so let me tell you a bit about extend this. This was just answering kind of is the graph connected, or in particular it was kind of returning a spanning tree, given these short messages from you. Let me kind of talk a bit about kind of k-node connectivity and k-edge connectivity next. So the results here is going to be to test k-edge connectivity, i.e., is it the case that between every 2 nodes there are k-edge distinct paths? Or equivalently, that every cut in the graph has at least k edges. It's going to be sufficient for each of you to send me roughly k polylog n bits. And then for the node connectivity results, I'm not going to be able to present this full result. The full result is like kind of, I'll be able to distinguish between graphs that are k node connected, or greater than k node connected, from ones which are less than 1 minus epsilon k node connected, using messages of this length. Okay, so I guess I do have a blackboard here, but this is my attempt to simulate a blackboard. So let's do k-edge connectivity first. So is the input graph connected after removing any set of at most k edges? So again, there's 2 main components. I need to show you a basic algorithm, and then I need to kind of argue that this can be emulated or analyzed in sketch space. So for k-edge connectivity, the basic algorithm is as follows. Take your graph. Let's pretend it fits in your hand. Take your graph and pick an arbitrary spanning forest of the graph. Rip it out. Okay? In the residual graph, pick another spanning forest. Rip it out. We'll call that one F2. Okay, less edges here now, so let's take another spanning forest and rip out another spanning forest, F3, and let's keep doing this k times. Okay? So this is just what I've said here. Now, it could be the case that the original graph was k edge connected, and yet these spanning forests I ripped out weren't all connected. That's certainly possible. But what is true is that if I just look at the graph formed by the edges, the total number of edges I've ripped out, F1 and F2 and F3 all the way up to Fk, then this graph is k edge connected if and only if the original graph is. Okay, I'm not going to prove that, but it's not too difficult. What I'm going to kind of dwell briefly upon is, well, how would we go about emulating this algorithm in Sketchbase? And I think it, again, illustrates this nice, like a simple but powerful property that the fact that sketches are from a linear compression gives you. So let's see that. So in the previous section, we learned how to construct we developed a sketch that would find me a spanning forest. Okay, so let M1G just be the projection of G that I could think about being formed just by taking all of your individual sketches that would allow me to find a spanning forest of G. Okay, we're going to actually do this k times simultaneously in parallel. So you're going to send me sketches such that I can find k independent spanning forests of the input graph. You might hope that just knowing k independent spanning forests of the graph is sufficient. If each one's random, like, maybe that's sufficient for us to determine this k edge connectivity. It might be. I can't pull off a proof. What I can do is as follows. Okay, so you've got the setup. Like, do what you did for allowing me to find one spanning forest, but let's just do it k times in parallel, kind of with fresh random bits each time. So if previously to find one spanning forest you were just sending me polylog n bits, you're now sending me enough information to do k times, so you're going to end up sending me k times polylog n bits. Okay. So the algorithm we're going to run in Sketchbase is as follows. So the property of the sketch we developed in the last section means that by looking at the collection of sketches you sent me, or essentially the sketch of the entire graph, I can find the spanning forest F1 of G. What I now do, somewhat similar to kind of Henri's suggestion and kind of peeling things off, is that, well, I look at the sketch that you guys sent me of the second sketch you guys sent me of the graph. I know what this random matrix was, so I can then apply that random matrix to the set of edges I've just found, F1, and subtract this vector from that vector. By linearity, this is the spanning tree sketch of G minus the edges in F1. And so the spanning forest I find from here, F2, is equivalent to just like I initially had the graph G, I ripped out F1, I looked at the residual and I ripped out another F2. Because of this linearity here, M2 is allowing me to find the spanning forest of G minus F1 equal to F2. And then we keep on going. So I've now found F1 and F2. I use the third sketch here of G. I subtract off the third sketch of F1, which I've constructed, and the sketch of F2. By linearity, this is the sketch of G minus F1 minus F2. So this is the residual graph after I've ripped out F1 and F2, and I can now find F3, etc. And I can do this kind of k times, and I will find a legitimate set of F1, F2, up to Fk. So again, linearity it results in a simple proof if you make everything formal, but I still think it's a little surprising. Was there any questions about that? Again, everything with high probability. One thing I'm going to need in a second when I come back to sparsification is you can actually extend this analysis to not just determine whether the graph is k edge connected, but you can actually recover a set of edges from the graph such that these edges have the property that if you remove those edges, the remaining graph leaves connected components with min cut strictly bigger than k. So you're basically kind of recovering the k-cores of a graph, if you're familiar with k-cores. Okay, so we're going to use that kind of that idea in about five or so minutes time. Okay. Okay, so let's talk about k-node connectivity first before we get to sparsification. So here's a graph that's still connected after you remove k nodes. So I'm not going to present the full results for the sake of this talk. I'm going to present a simplified result. And the simplified result is you see your stream of okay, sorry. Let's stick with the communication setup. So you have your address book. You send me your sketches of your address book. I'm not going to answer the question, is it the case that for every set of nodes I could delete, is the graph connected? I'm going to say that, well, let's suppose I have a specific set in mind, S, which you guys don't know. Okay, so you send me your sketches, and then I go for this specific set, S, I'm going to be able to determine whether the graph would remain connected if I deleted all the nodes in S. Okay? And S is a set of size at most k nodes. Okay. So everyone happy with this simpler version of the problem? So for node connectivity, it's really for all sets at most k that I could delete, is the graph still connected? Like if in this setup where I'm just saying, let's suppose I have one particular set S in mind. You guys don't know it when you do your compression. And I need to answer the question, like, is the graph still connected after I delete nodes in S? Okay, so the basic algorithm is we're going to do something roughly k squared log n times. So for each I, let vi be a random set or a subset of nodes. Okay, so every node in the original graph is present in vi with probability 1 over k, and all nodes are independently sampled. Okay, so I have now v1, v2 up to vr. Each is a random subset of nodes. Okay, and then let fi be a spanning forest of the induced graph g square brackets vi. So I'm going to use g square brackets vi always to refer, in the rest of the talk, to refer to an induced subgraph on some subset of nodes. Okay. So this is the algorithm. So this generates f1 up to kind of, oh, pardon me, this should be fr. And so when I know my s that I'm considering deleting, I'm going to check whether of the edges I've got, if I delete all edges or all nodes in S, I'm going to test whether this thing is connected. And then I'm going to claim that, I'm going to use the result that with high probability, G remove, and then you remove the nodes in S, is connected if and only if the graph here is connected. Okay, this is not so trivial. I'm going to prove that. But before I go on, I want to argue that, like in the same way, kind of you could use those the spanning tree sketch that I presented in the first section for edge connectivity. Like you can do the same thing here to work out your spanning forest fi. So you can actually find each of these spanning forests using a small number of bits for each player. Okay, so proof of the lemma. So I'm proving that this algorithm collects you a bunch of edges, f1, f2, up to fr, and I want to prove that, or this sketch a proof, that this graph is connected if and only if that graph was connected. So let's do that. So first direction, if G set minus S, remove the nodes in S, is disconnected, then this thing's disconnected. This essentially just follows because this is a subgraph of that. This has all. So this has all the edges here, plus some more, the ones that didn't go into one of the FIs. Okay. So it's certainly true that if G set minus S is disconnected, then this thing should be disconnected. There's no way this could be connected if this is disconnected. Now, this is the slightly more challenging side. So that G set minus S connected implies that the set of edges I've connected set minus S is connected. So to do this, okay, so let's assume that this is connected. And let's pick an arbitrary pair of nodes, U and W. Okay? And if this thing is connected, then there should be a path from U to W. Let's say S was up here. So there should be a path from U to W that avoids S. Okay? So let's say it goes via V1, V2, V3, V4, and etc. Okay? Okay. Now pick an arbitrary pair of nodes along this path. Let's say these two guys, V3 and V4. Okay? I claim that with high probability, there is one of the subsets of nodes, Vi, that includes V3 and V4, but doesn't include any nodes in S. So claim, with high probability, there exists Vi. Oops. Yes, I'm so used to following there exists by a for all that it's hard to write a there exists a V. There exists a Vi such that V3 and V4, say, these two guys are in Vi, but Vi doesn't intersect S. Okay. I'm not going to go formally through the proof of that, but it basically follows because remember, like when I was generating Vi, I was subsampling every node with probability 1 over k. Okay. There's at most k nodes here, so this is S. K nodes. So if I'm subsampling node edges with probability, okay. No, I'm not going to prove it. It's not actually true. Actually, it is true. Pardon me. Okay, let me get back to the intuition for why it's true. So I'm subsampling nodes with probability 1 over k. So when I generate V1, say, there's a constant probability I pick none of these guys. Okay? Because I'm subsampling with rate 1 over k, there's at most k things here. So there's a reasonable chance I pick nothing here when I'm generating V1. And the probability it includes this guy and this guy is 1 over k squared. So when I generate V1, it has this property that V3 and V4 and V1, but V1 is disjoint with S with probability roughly 1 over k squared. So if I repeat this process R times, and if R is roughly k squared, then I can say with high probability. Okay. But what's the import of this? So I say that there's a Vi that includes this pair, two nodes along the path with high probability. Well, what this means is that, remember, for each Vi, we constructed a spanning forest. Now, if the edge Vj to Vj plus 1 was if both these nodes were sampled, then this edge is in the induced subgraph. No guarantee this edge is in the spanning forest we find, but if this edge between Vj and Vj plus 1 was in the induced subgraph, in the spanning forest there must be a path between Vj and Vj plus 1. So this result implies that in some Fi, there is a path from V3 to V4, and maybe goes somewhere crazy. It doesn't intersect S, and it joins V3, V4. And so applying the union bound across all consecutive pairs in this path, you can argue that by stitching up these paths, you get a path from U to W that avoids S. And then by taking the union bound over U and V, you can argue that there is a path between U and V for every U and V that avoids S in the graph amongst your sampled edges. Okay. So my second half of the talk is shorter. But I think it's natural maybe if I spend 5 more minutes talking about sparsification, then break, and then return for matching. Is that okay? Sounds good. Okay. So sparse files, we can, actually it's not even going to be 5 minutes. I probably spent more time asking your opinion than I just spent like, just finishing off the section. So for sparse files, I'm not going to kind of talk about the spectral sparsification results in this talk. I'm just going to kind of give you enough details to give you an idea for what's going on for the approximating every cut within a factor 1 plus epsilon using a message from each of you of roughly 1 epsilon squared polylog n bits. So, I know. The idea for graph sparsification, if you haven't come across it before, I know, I like to sometimes introduce as follows. Like when you have some music, there's a natural way to compress it. MP3 file or some other type of audio file format. When you have a piece of a picture, a photo, or a painting, naturally we compress it as JPEG. So even before sketches and sampling and particular computational models, there is the kind of equivalent to these things for graphs. You could argue would be spectral sparsification. So the idea is that you start off with your initial dense graph, that there's a way to transform it into a much sparser graph. Like maybe this thing's unweighted and this thing's weighted. So no matter how dense it is, you can transform it into a sparser graph using where the number of edges is roughly proportional to n, such that in this graph, if you measure the size of any cut, it'll be within a factor 1 plus epsilon of this same cut here. And similarly, if you measure kind of the eigenvalues or mixing times or any nice spectral properties, here you'll get a very good estimate of what it was in the original graph. So that's the idea for spectral sparsification and cut sparsification as well. So cut sparsification is if it only preserves cuts. Spectral sparsification if it preserves cuts and some other stuff. So the main idea for the sparsification via sampling is going to, so this is a more recent way of describing what's going on that appeared in the PODS paper last year, which I think is significantly simpler than the way in another group initially presented our algorithms. So Karger has this result, and this is something that you can, it's probably a hard result to come up with, but it's actually an easy result to say, for example, teach to a class, is that suppose you have a graph. Okay, this is actually a corollary of what Karger said, a corollary for our own purposes. So suppose you have a graph. It's a bunch, maybe it's kind of one big component, or maybe it's multiple connected components. But I promise you that every connected component, the min cut is at least this. Or equivalently, that every non-zero cut of the original graph G has this size. Okay. Then an application of a theorem that Karger proved was that if you subsample every edge with probability 1/2, then, well, obviously, if you take any particular cut in the graph, in expectation, the number of edges go down by exactly 1/2. But assuming this condition on the min cuts, what you can show is that with high probability across all cuts, so with high probability for all cuts, not for all cuts with high probability, with high probability for all cuts, the cut changes by not exactly a factor 1/2, that'd be too much to hope for, but within a factor 1 plus or minus epsilon over 2. So the fact that things go down by 1/2 is obviously an expectation by linearity of expectation, so you can actually prove a kind of concentration here. Okay. And then I don't want to go through all the details, but really, this, if you fully understand what I'm going to say here, you could reconstruct almost all the details. The idea for constructing sparsification in this kind of communication or streaming or sketching setup is as follows. So you define a sequence of graphs. G naught is your original graph, G1, G2, G3, up to about G log n. And Gi is basically formed from Gi minus 1 by, I don't know, I feel like my laptop's hinting here. Gi is formed by Gi minus 1 by deleting each edge with probability of half. Okay. So now what so remember I asked you to put a result in your back pocket that we'd use later. So an extension of this k-connectivity stuff was that we could find a set of edges whose removal left you with connected components with high minimum cuts. That's exactly what we're going to use here. So let W of Gi be the set of edges whose removal leaves a graph where no non-zero cuts where non-zero cuts have at least this number of edges. Okay, so this is like if you're all out there, like we can simulate protocols on not just the original graph G, but also G1, G2, G3, G4, these kind of log n graphs. We're going to simulate that k-edge connectivity protocol in each of these log n graphs, and I'm going to be able to find a set of edges whose removal leaves connecting components with a reasonable number of edges. Okay, and so yeah, so we could find all these sets of edges and roughly with messages from each of you with roughly 1/sin² log n. And then the idea is that the graph G1, this thing where everything was sampled with rate of half, combined with this set of edges, allows us to approximate all cuts in G0. Okay. G2, along with all sets of edges in WG1, will allow us to approximate all cuts in G1. G3 and WG2 will allow us to approximate G2, etc., all the way down to the final level where there's no edges, or where all the edges will be in WG log n. Put that all together, and you'll be able to get cut sparsification. Okay, so thanks very much for paying so much attention. Matchings will be a shorter section, maybe under half an hour. That I'll talk about after people have had a break.
Let us take 15 minutes.